Now, building on top of our previous lecture, I'm going to do a slightly more advanced experiment, and this experiment is only done to convince us that the electron, when we try to find a locate an electron, the electron is actually behaving as a wave, or the probability of finding an electron is actually the same as that of a wave. Now, again, I'm going to pick my singer. My singer over here is singing, and he's producing a sound wave, and that sound wave is traveling in a straight line, and it spreads out. The sound wave spreads out throughout the room. Now, in the first room, there are two rooms now. In the first room, there are two doors, there are two openings. So let's say this here is one of the openings, and this here is the second opening. So there are two doors which lead to the second room. So the second room is over here. Now what happens is that the sound wave which was traveling in the first room has two choices. It can exit the two doors, and it would do that simultaneously. Waves, if I am speaking in my room and there are two doors to the room and I'm talking, then my sound wave is going to exit the two rooms simultaneously at the same time. So the waves exit the first room and they travel into the second room, and when they pass through the door, they diffract. So if you look carefully, these orange lines over here, these represent the sound waves after they've exited one of the doors. So the orange lines are the ones which show the sound wave traveling from one of the door into the second room, and the red lines, the red waves, are the ones that are traveling from the first door. So the sound wave is going to spread out. It's going to exit the two doors. It's going to diffract. It's going to move in all sorts of different directions, and the two doors are going to produce two separate sound waves. Now what happens now is that the two sound waves, one coming from each of the doors, they're going to interact with each other. And that is called, the term that is used is called interference. So it's called interference. Because what happens is that the singer was producing one sound wave, but as soon as it passes through two of the doors, the sound wave splits into two separate sound waves, one represented by the orange line and one represented by the red line. And the two waves are going to interfere with each other, and there are two types of interferences or superpositioning. One is called the constructive superpositioning or constructive interference. And what happens in constructive interference is that the two sound waves, they add up, and when they add up, you're going to hear a louder sound. So if the two doors, the sound waves coming from the two doors, if you're standing at the other end and at your position, the two sound waves are adding up, they are meeting in phase, which means that you're going to hear a louder sound. The second interference is called destructive interference. What destructive interference would be, that the two sound waves that are emitted by the two doors, if they're not meeting in phase, one's crest and the other's trough are meeting, that means that they're going to cancel each other out. So the two types of interference, if the two sound waves are meeting in phase, that means that they're adding up. So I can draw two sound waves, one for constructive interference. So let's say I have this sound wave, and there's another sound wave, and I'm standing at a position observing the two sound waves reaching me. And what I mean that they're meeting in phase is that the sound waves are exactly at the same time they're in phase. The troughs are meeting and the crests are meeting, which means that the two sound waves are going to add up. So in this case, they're going to add up. But vice versa, they can cancel each other out if you're standing at a position where one sound wave looks like this and the other sound wave reaching you looks like this. Now these two sound waves are not meeting in phase. So in this case, the interference is going to be a destructive one. So this is an example of two sound waves that are meeting out of phase. And this is an example of two sound waves that are meeting in phase. So if they're meeting in phase, you're going to hear a louder voice. If they're meeting out of phase, you're going to hear a lower voice. They're going to cancel each other out. Now, if you look at the pattern the waves are forming in the second room where the interference is happening, you're going to observe that if you look at this point over here and this point over here, right in the middle, you can see that the yellow lines and the red lines, they are meeting in phase. They are meeting in phase, which means that the sound wave at the center is going to get added up, and there is going to be constructive interference taking place. They're meeting exactly in phase, which means that you're going to hear a louder voice. So anyone who's standing over here, let's say there's a person standing over here listening to the singer, he's going to hear a louder voice. Similarly, if you look at these points over here, the waves are meeting in phase, which means that any person standing over here as well is also actually going to hear a louder voice. So a maximum amount of sound is going to be heard because the two waves coming from the two doors, they're going to get added up. And if you can find a lot of places in the room where a louder voice could be heard. So here's another area, another region. So if you're standing at the end of the room, so you're going to hear a maximum voice, a louder voice in this area. Now, similarly, in exactly the same way, there would be regions where the sound wave would not be that loud. So if you look at this center point over here, and let me draw a line. So if you look at the waves, they're not meeting at any point. The two waves, the orange lines and the red lines, they're not meeting at any point, which means that constructive interference is not going to be taking place. So you're going to hear a lower sound. It won't be that loud because a destructive interference is taking place. Similarly, in this region over here, you're not going to experience a loud voice. A minimum amount of, or a lower voice would be heard because the sound waves are cancelling each other out. Similarly, this area over here, at any of the points, the sound waves are not meeting in phase. So again, not a very loud sound would be heard. Similarly, over here as well, they won't be meeting in phase, so not a loud sound would be heard. Now you can see what the pattern is forming. What the pattern suggests is that if there are two slits, or let's say there are two doors to a room, the type of sound being heard in the second room, it would be an area where a maximum amount of sound would be heard, and there would be an area where a minimum amount of sound would be heard. So there would be a pattern. So if you want to locate where the singer's sound is present, or there's a high probability of finding the singer's sound, then it would be present in a larger amount in certain areas, and the probability of finding the singer's sound would be lower in certain areas. Now what I've done is that I've drawn a probability function of locating the singer's sound. So there would be areas where the singer's sound would have a higher probability, or the sound that you're going to experience that's going to be much louder. So there would be areas where there's going to be a lot of sound waves coming, and there would be areas where there would be minimum sound waves coming because the sound waves are cancelling each other out. So there are regions where minimum amount of sound would be heard, and there would be regions where maximum amount of sound would be heard. So if you're trying to locate where the singer's sound is going to be in the second room, then you can describe it with a probability function. And this is exactly what we're going to do with electrons as well. Now I'm going to repeat the Young's double slit experiment, but this time I'm not going to use my singer. I'm going to use electrons. So I have this gun and I'm shooting electrons as this double slit. So there are two slits open in the first screen, and if an electron was a particle, what's going to happen is that the probability of finding the electron would probably either move from one slit or the other slit. So what you're going to observe is if it was a particle. So I'm assuming that if it's a particle, what the behavior of an electron would be, it would either move from one of the slit and end up on the other side, or the electrons being short would move from the other slit and they would end up at the other end. So if an electron was a particle, there would be a very high probability of finding electrons in two places. One of the place, the maximum probability of finding an electron would be over here, and the other place where there would be a maximum probability of finding an electron would be at this position. So if you're trying to locate electrons and the person at the other end is trying to shoot, so if this is you're standing over here and you're trying to catch those electrons, and those electrons are coming from two slits, and the person at the other end is shooting those electrons. So the electrons could either exit one slit or the other slit. So the two areas where the probability of finding an electron would be maximum. But here's the problem. The problem is that when you try to locate the electron at the other side, there's going to be a region of higher probability in the center as well. Actually, the region of highest probability would be at the center, where there would be a very high probability of finding the electron. Now, that's an anomaly. If it was a particle, that's impossible, because particles do not diffract, which means that it's impossible that the electrons suddenly change direction. And most of them say that, that we like the middle part, we want to be there. So it's actually impossible to imagine an electron as a particle when you see this kind of behavior, which would probably suggest the previous case, the singer's sound. If you remember that experiment, the only way this pattern is possible is that if an electron is actually behaving as a wave. So the problem is the electron does all those collisions. It has a specific mass. It has a specific charge. It's always behaving as a particle. But when you try and look for an electron, the pattern that you observe is those of waves. So this is what wave-particle duality is. And the wave function of an electron only applies when you try to locate an electron. So the region of high probability of finding an electron, if you use the double slit experiment for an electron, there would be regions of maximum probability of finding an electron, and there would be regions in the middle which would have a minimum probability of finding an electron. So there would be areas of high probability and there would be areas of low probability of finding electrons. And the wave function would exactly be similar to this wave function that I've drawn over here. It would be similar to this wave function. So a wave function gives you regions of high probability where there's a very high chance of finding an electron. So remember, an electron is a very non-localized particle. You're going to think of an electron as a particle, but when it comes to locating an electron, its behavior resembles that of a wave. So electrons would be found in areas where there's going to be very high probability of finding an electron, and that would be described by a wave function. So this double slit experiment, when you apply it to an electron, it would be very similar to the experiment that we did previously with the singer's voice. In the other room, in the second room, there would be areas where there would be a very high probability of finding the singer's sound. There would be very loud singing going on in those areas. And there would be areas where the singer's sound would be barely audible, which means that the two waves emitting from the two doors would be cancelling each other out. So if you try to locate the singer's sound, there would be an area of maximum probability and there would be an area of minimum probability, and the same applies to an electron as well. If you look for an electron, there would be certain areas where there would be a very high probability of finding an electron, and there would be other areas where there would be a very low probability of finding an electron. So the location of an electron would always be described by a wave function, and it would be a mathematical wave function.